7.2 was all about graphing exponential functions, and 7.1 was kind of an introduction to exponential functions, and then we did some financial problems with the compounded formulas, whether it was compounded monthly, yearly, or continuously. And then we looked at graphs of exponential functions. Now we're going to look at logarithmic functions, which are essentially going to be inverses of exponential functions. So whenever we introduce a new function, we also look at its inverse if possible. So we'll do a little recap here. I'm going to go over some of the important things and maybe do a couple of examples. First important thing is being able to convert between logarithmic and exponential forms of the same expression. So if you have an exponential expression where you have a number or something raised to a power equal to something else, you can convert that to logarithmic expression. And how that works is we'll see some of the properties of logarithmic expressions in 7.5. But before we get to that, essentially how this works is if you start with an exponential function and you kind of want to get this this y isolated, there's not a real nice way of doing that because we don't have any tools for that. So if we had something, I guess down here, if we had something like this and we wanted the 2 to be alone on one side equal to something, then the way we do that is we move this 5 because it's the base of an exponent, the base of an exponential expression, we take it to the other side as a log base. So when this 5 shifts over to the other side, it shifts over as log base 5 of 25. Right? And then that conversion from exponential to logarithmic form also allows this 2 to come down from the exponent so that it's no longer an exponent. Right? So that's moving in one direction. The 5 moves to the other side as the base of a log. Going the other way, going from a logarithmic expression to exponential, we do the exact opposite. So this base of this log, or the whole log, kind of shifts to the other side, and then it pushes this 2 up into an exponent so that the 9 is left alone on the left side, and the 3, the log base 3, moves to the other side as a 3 squared. And this is obviously not groundbreaking. 3 squared is equal to 9, right? That's not a weird expression to kind of, we're not trying to prove anything here. We're just getting used to the idea that if you have a log base number on one side, you can shift that to the other side as an exponential expression, right? And then the same thing here. This is not, there doesn't seem to be a reason for doing this process here because 5 squared is 5 times 5, which is 25, which is equal to 25. So we're not actually doing anything to prove anything, or we're not trying to solve for anything here. We're just converting between logarithmic and exponential form. Right? So this is just to get you used to the idea of going from this form to this form and back to the other form. Right? So we should be able to switch from one form to the other. Okay, and that's going to be a useful tool for all of the properties of logs that we're going to look at. The first thing it's going to be useful for, though, is when we actually want to solve or evaluate logarithms. So if the question was something like 2 to the 4th power, we know how to evaluate that. That's just 2 times 2 times 2 times 2, which is 16. Right? We know how to evaluate an exponential expression, but can we evaluate a logarithmic expression? And the best way to do these for now, before we get to section 7.5, is to set them equal to set them equal to a variable, such as x, and then we'll try to figure out what x is. And if you know how to convert from logarithmic expressions to exponential, we know that we can take this log base, move it to the other side, and push this up into an exponent, so that we get 64 equals 4 to the x power. Right? When we convert from logarithmic form to exponential form, we see that, and now the question is, what power of 4 equals 64? That is the question that we're being asked here. We're trying to find x because x is equal to our original expression that we started with. So what is this x equal to? Well, that is equal to 3 because 4 times 4 times 4 will be 64. Right, so the answer is x equals 3, which means the original answer, the original expression, remember there was no x in the question, I came up with that. So we don't really want to give the answer in terms of x, but the answer is just a simplified form of log base 4 of 64, which is equal to 3. Right, so it simplifies down to 3. And you can kind of skip this step if you get used to the idea of asking the correct question. So when I look at this, the question is what power of 4 equals 64? Which means when I look at something like this, the question is going to be what power of 2 will equal 1 over 32? Right, so the question will be what power of 2 equals 1 over 32. And you have to figure out what exponent can I put on a 2 so it's 2 to that power and it equals or simplifies to 1 over 32. Right, so that's how we evaluate logarithms. You can either go this way and convert and then figure out what this exponent is going to be, or you can straight up ask the question from looking at the logarithmic expression. Any questions so far?
Yeah, for letter C, how would that work? So it would be what power of 121 equals 11?
Yeah,
Or can it just
it is. Yeah, so 121. I guess let me write it the other way. If I call this equal to x, then I have 11 equals 121 to some power, and we're looking for that power. And oh, sorry, not 125. 121 to some power x, and there is a way to get from 121 to 11 by using a power. If you notice, 121 is a power of 11, right? 11 squared is 121, but that's not the relationship we're looking for. So how you would get from 121 to 11 is by square rooting it, right? Because 11 squared is 121. So if I were to start with 121, I would need to square root it to get back to 11, right? Knowing that fact on the side there, we should know how to convert square roots into powers. And so the power in that case would be 1/2, right? An exponent of 1/2, or 121 to the 1/2 power should give us 11, because that's square root of 121. Does that answer your question?
yeah, it does. Thank you.
Right, so the answer in that case would be 1/2. So that's going to happen sometimes. And then this one's also weird. I know I just wrote the question, but this one's also weird. If I take 2 to some power x, how do I turn that into 1 over 32? Well, I know I can turn the 2 into a 32 by putting a power on it, because that is a power of 2. It's 2 to the 5th. But how do I get it to become a fraction like this? And that's by the use of negative exponents, right? If x is equal to -5, I mean, that's going to be the answer. But if I take 2 to the -5th power, that gives me 1 over 2 to the 5th power, because that's what a negative exponent does. And that gives me 1 over 32, right? So you'll have to get creative with Square roots, sometimes you'll have to get creative with negative exponents if you need to create a fraction of some kind. So yeah, they're not always as straightforward as this one, where it's just obviously that's 3 4s make a 64. Cool. Any other questions? Okay. Common logs. We have so far seen logarithms with a certain base, but the base 10 logarithm is used very often. So we're going to give it a name and call it a common logarithm and not write the base on it. There are multiple reasons. 10 is tedious. It's two characters extra to write. And it's used a lot. So we're just going to call that log. Right? If you see log with no base attached to it, then assume that it's log base 10. Right? So instead of writing log base 10 over and over again, we're just going to simplify that to log. That's all that's saying. You still do everything the same way. You just imagine that there's a 10 as the base, right? You can still set this equal to x. You can still move that base to the other side and shift this up into the exponent. So 1 equals 10 to what power is the question. And in this case, it's going to be 0 because anything to the 0 power is 1. So log of 1 simplifies to 0. Right? And you can do that for any kind of expression that just has the common log. The other log that's used a lot is a log base e. So instead of using writing log base e over and over again, we're going to simplify that to be the natural log written as ln. I'm pretty sure it comes from a different language. It's probably some log natural translation. So that's what ln stands for. And whenever we see ln, it is equivalent to e to the y equals x. If we take this ln, it has a base e, we shift it to the other side, the y shifts up into an exponent, and that's where we get the e to the y, and then the x is isolated down below. So if we were to do the same thing with oh, that one's interesting. Part D is a very interesting question because we haven't really talked about properties of logs yet. So if I were to try to do the same thing here, set it equal to x, what we cannot do is we cannot shift this over to the other side yet because this 25 is kind of in the way. We don't know what to do with the 25 while we convert from logarithmic to exponential form. So we're going to get rid of the 25 first. We're going to divide both sides by 25. So we get ln of e to the 2/5 equals x over 25. And then we can take this ln, which is log base e, move it to the other side, shift the whole other side up into an exponent. Right, let's when this ln goes to the other side as a e, it shifts the whole other side into an exponent, so we get e to the 2/5 equals e to the x over 25. And if you get an expression like this, or this equality, this type of equality, both sides are some kind of power of e, right? If I were to tell you that, like, 13, this is a separate problem. But if I had something like 13 to the 2 times 17 power is equal to 13 to the x power, these two sides would only be equal because the bases are equal. These two sides would only equal each other if my exponents were the same. So then we can go from this to 2 times 17 equals x. Right, this is just a little mini example on the side. Therefore, x would have to be 34, for example. Right, this is a little side example. exponents work that way. If the bases are the same on both sides, then the exponents also have to be equal to each other. So if I have e to some power on this side, e to some power on this side, those two powers have to be equal to each other, which means we can get rid of the bases and say that 2/5 has to equal x over 25. And we're not working with any kind of exponential form anymore. This is just a fraction equal to a fraction. We can solve that for x. We multiply both sides by 25, and x will equal 10. Right, which means this expression here, let me actually box that. This expression here simplifies to 10. Any questions on any part of the common log or the natural log? All right, that completes just like the introduction to logarithmic functions. 7.4 is about graphing, and I'm going to go straight to this properties or characteristics box on page 176. We're going to treat these kind of like how we treated exponential functions and how we graph those, but instead of we don't really call them growth or decay. Remember, we called exponential functions either growth or decay, but they kind of look similar to exponential functions. That's not a coincidence. These are inverses of exponential functions. Therefore, their graphs will have the same similar shape, except they're reflected because that's how inverses work. So now we have a vertical asymptote at x equals 0. So we have a vertical asymptote at x equals 0. And a couple of key points are the 1, 0 and the b, 1. So as long as you graph those 2 points from log base b of x, and then the general shape is decided by the b, which is the base of your log. The general shape is decided by b, just like in exponential functions. In this case, if b is bigger than 1, then we have an increasing function going from left to right. And if b is between 0 and 1, then we have a decreasing function. Kind of like we did with the exponential functions, right? B being greater than 1 was a growth function. It was getting bigger from left to right. It was a different shape because it was doing this, right? That was the exponential version of that. But if b is less than 1, if it's between 0 and 1, then we have a decay function which goes down this way. Domain and range you should pay attention to, but not necessarily have to worry about when you're graphing. Mainly these 3 things will help you graph, right? The horizontal intercept is always at 1, 0, and that is the reflected form of 0, 1, because remember for exponential growth or decay functions, they all went through 0, 1. So the counterpart of that, the reflection of that, would be 1, 0. So horizontal intercept at 1, 0, and then the key point is going to be at b, 1. So as long as you graph those 2 points and then put your vertical asymptote at 0, you should easily be able to graph logarithmic functions. Domain-wise, the domain of logarithmic functions is restricted because the range of exponential functions was restricted. So when we switch from exponential to logarithmic, we get a switch in the domain and ranges. So we do have to worry about domains. And the main thing here is that the domain of the domain of logarithmic functions are only positive real numbers, which means we take whatever is inside of our logarithmic function, and we take that and we say that whatever is in there must be a positive real number, so greater than 0. Right? That is the setup for finding the domain. and then whatever that is, you solve like you would solve any inequality. We're going to subtract 3 on both sides. This one is pretty straightforward. X must be greater than -3. That is our domain. We can write that in interval notation, -3 to infinity, or we can write it as a inequality. X is greater than 3. So either one works for your answer, right? So you take whatever's inside the log. The base doesn't matter. Regardless of the base, you can take whatever's inside the log, set it greater than 0, and then solve for the domain that way. Okay, so that finishes graphing logarithms. Are there any questions on the graphs? Or the domain?
Yeah. Will it always be set greater than 0?
Yes.
Okay.
It may end up being like after when you solve it, it may end up having a less than symbol, because remember, if you multiply or divide by a negative sign along the way, you have to flip the inequality. So I'm not saying the answer is always going to be greater than, but the setup is always greater than 0. Yes.
All right. Cool.
Yeah. So if you see a less than in the answer, then that's because there was a negative of some kind. Like this example, I can already tell because there's a -2 in front of the x. We're going to have to divide by -2 at some point, and it's going to flip the inequality. All right. And then the next section is going to be properties of logarithms. Today we're going to talk about the first 3 on here: the product rule, the quotient rule, and the power rule. And these are kind of scattered in the section. Oh, actually, we have some stuff before the product rule. Okay, so these are also properties. Because of the way that exponential functions and logarithmic functions kind of undo each other, because they're inverse operations, we have these certain properties that show up. That's essentially a property where if you have a log of 1, doesn't matter what the base is, it's going to simplify to 0. And then a log base b of b is going to be 1. If you want to think about these are pretty easy to solve on the spot, because remember, this one here asks the question, what power of b equals 1, right? And no matter what b is, if b is 217, what power of 217 equals 1? If I take anything, any b to the 0 power, it'll equal 1. So that's why the answer to that question is 0. And then this one asks the question, what power of b is b? Which is kind of a weird question to ask. But what power do I take b to get b? And that's going to be 1, right? So that simplifies to 1. Right, so those are kind of base properties that we can now use to simplify things. Another one is this one, which again, if you ask the question, it says what power of b is equal to b to the x power. So essentially we can think about it as using this formula. The log base b of b cancels out, and the answer is x. And then a similar thing happens here. This one's a little bit more involved to get to it, but if the base of your exponent matches the base of your log in either orientation, so if you have the log first and then the exponential, or you have an exponential and then the log in the exponent, as long as these bases match up, they essentially cancel out and we just get x. So these are interesting ones that we can use when we're simplifying expressions. So these 4 you need to know. solve the equation. Right. And then this is not necessarily a property, but kind of like how I did the example with this example over here on the side where I had 13 to some different powers, and we said if 13 is to some power equal to 13 to another power, then those exponents must be equal to each other, right? In a similar fashion, if I have the same exact log on both sides, then we can get rid of them, because if log base 3 of 3x is going to equal log base 3 of 2x plus 5, then those two things, the 3x and the 2x plus 5, must be equal. Right? So we can get rid of these logs because they're the same. Now, slight, like something to be careful about, I'm not dividing by log, right? It's not something that we're dividing by. We're just getting rid of it because it's the same thing on both sides. The way we're getting rid of it is kind of hidden in the backgrounds. We're doing some exponential form. We're converting to exponential form and then back into simplified form to kind of get rid of the logs. But just to keep in mind, if the log bases are the same on both sides, you can just get rid of the logs, right? As long as they're identical on both sides. Right, so then you can say 3x equals 2x plus 5 and then solve from there. All right, we had a product rule for exponents where if we were to multiply two exponential expressions with the same base, we would add those exponents together. Hopefully you remember this property. This is an older property, right? Old property that we already know. And this is the new property that is essentially the analogous property in that has to do with logarithms. So if I have two things inside of a log multiply together, so if I have log base b of m times n, we can expand that into a sum. Right, so that's a property that I guess it's down here again. I don't really want to highlight that one. In the box here, we have the same thing. That's the property we want to be able to use, right? If things are multiplied inside of a log, we can expand it, and notice that this log is appearing on both things that we expanded and that we're adding together, right? So the single log turns into a sum of logs, and it splits where the multiplication is, and it turns into addition. So if I were to expand, if I were to expand something like this, I find what things are multiplied together in here, and I split at the product. So this we can split as log base 3 of 30x plus log base 3 of 3x plus 4. Right, so I can take this product here, the 30x times the parenthesis, and split into multiple logs added together. Right, that's the easy split. There's actually another split in here that we can do because there are two things multiplied together in this log, right? So we can split the 30 times x as well into another sum. So we'll have log base 3 of 30 plus log base 3 of x plus log base 3 of 3x plus 4. Now we can't split this one because this is not just 3x, this is 3x plus 4 as an expression. So this is two things added together, not multiplied together. I know the 3x is a product, but the 3x is not the only thing in here. Because there's a plus 4, we can't split this any further. But this would be our final answer here for the expanded version of the original expression. Which means this
week, unlike the many others before it, actually didn't disappoint. GTA 6 is real. It was just
Eduardo,
announced by
can you mute?
Rockstar on X, and we now even know when exactly the trailer will drop. On the official X.
Okay. This is not a product. This is a sum of terms, and we can't split these until we have some kind of product in here. What we might be able to do is factor this, if it does. And if you factor it, you'll end up with some kind of log base 6 of two parentheses or two factors multiplied together, maybe with like a 3x plus something and an x plus something. In that case, we would be able to split after that fact. But until you factor, you can't expand that one. So if I were to factor that, what's 28? 7 times 4. So if I put a plus 7 here and a plus 4 here, I think that works. Yeah, so now you can expand into log base 6 of 3x plus 4 plus log base 6 of x plus 7. All right, so before we can expand, it needs to be a product. This is not a product, this is a trinomial, right? So, but if once we write it as a product, we have two things multiplied together. This is essentially like the, this is my m, this is my m, and this is my n. So when I split this up, I get log base 6 of m, and then plus a log base 6 of n, right? I'm using m and n from this formula here, the product rule. Okay, that's the product rule. The quotient rule is that it's kind of similar to the product rule, but if we have division inside the log instead of a product, we can split into a difference. This is the quotient rule. So if I have a quotient here, we can expand into multiple logs, but they're subtracted from each other. So expanding something like this fully requires a couple of steps, because while we have a quotient in here, we have a top expression and a bottom expression, which means we're going to split into a difference. So the first thing we would do is we would say log base 2 of the numerator, so 15x times x minus 1, minus log base 2 of the denominator, which is 3x plus 4, 2 minus x, and we wouldn't stop there because it says to expand completely, because now we no longer have any quotients, but we do have products, right? We have things being multiplied together. These two are multiplied together. There are 3 things being multiplied together here. So those are going to expand into a sum of logarithms. So we're going to have 1, 2, 3, 4, 5 logarithms added and subtracted from each other as a result here. Firstly, I'm going to expand this first log here. If I expand that, I get a log base 2 of 15 plus log base 2 of x plus log base 2 of x minus 1. Right, that's all of that expansion from a single log. We get 3 separate logs added together. And then minus this one log is going to turn into 2 logs because there's a product. But we have to be careful because this one log had a minus in front of it, right? So the best way to do this is to say, I'm going to take this log and I'm going to expand it on the next step, but I'm going to keep it in brackets because that minus needs to be in front of this whole expression. So when this expands, we end up with log base 2 of 3x plus 4 plus a log base 2 of 2 minus x, but all of that is inside of a bracket with the minus in front. So this minus, if you wanted to get rid of those brackets, this minus would need to distribute to the two terms. You can kind of avoid doing all that work if you expand in one step and kind of follow the rule of numerator factors are positive logarithms and denominator factors are negative logarithms. So if we follow that rule, we can kind of go from this first expression immediately to the answer. So if I were to do this in one step, I would say any factor in the numerator, and I'm going to isolate them by drawing boxes around them. So I have the 15, I have the x, and I have the x minus 1. Those are my numerator factors, and my denominator factors are the 3x plus 4 and the 2 minus x. Right? So I have 3 factors in the numerator and 2 factors in the denominator. That means I'm going to have 3 logs added as positives and 2 logs as negative logs. So when I write this answer here, I can say a positive log base 2 of 15 plus a positive log base 2 of x, a positive log base 2 of x minus 1. And then for the denominators, I say a negative log base 2 of 3x plus 4 and a negative log base 2 of 2 minus x. So I can go straight from the original expression. We can go straight from the original expression to the expanded, fully expanded form by just following this simple rule of numerators are positive logs and denominators are negative logs. Any questions on expanding? Finally, the last thing we're going to look at is called the power rule. And this is, I think this is the most used property of logs, where if you have if you have any kind of exponential or some kind of exponent inside of a logarithmic expression, you can take that exponent and you can move it to the front of the log as a product. So we see that we go from this to n times log base b of m. Right? We take that exponent, we can push it to the front as a product. So we could take something like this, for example, log base 2 of x to the 5th. We can take this 5 and move it to the front of the log as a product. So that 5 will be in the front, times log base 2 of x. Right, and we can go the other way as well. We can, if we have something multiplied by a log, we can take this, if we wanted to go the other way, we could take this number in the front, or whatever is in the front, and put it back up as an exponent of whatever is inside the log. Right, so that's how we go from one form to the other. So the power rule goes both ways. If I wanted to do the other way on this example here, 4 times natural log of x, I could take this 4 and I can push it back up into the exponent of that x. And we can rewrite this as natural log of x to the 4th power, where x to the 4th power is inside of that natural log. And we're going to stop there. Are there any questions on the power rule?